Let me start by talking about the homework assignment. So homework number 5 is the following, and I hope everybody's seen it. It's perhaps requires more, it may be a little bit more challenging for some of you. It requires that we work on a time series prediction. Okay, and basically this is really about IoT, which is what this course was trying to focus on. And what I've done is I've taken some real data based on sensors using something called a wireless sensor network. For those of you who are not familiar with what a wireless sensor network is, it's basically sort of an older version of an IoT and Internet of Things, where you have sensors and they're connected over a wireless network. And in this particular case, the sensors were deployed. I'm not sure exactly where we had deployed this, but they were in different rooms and so on. And each one of the rooms has an ID. And I've given you 2 versions of this database, version 3 and version 4. And the idea is that you look at a particular room. So that's room number 53 that you're supposed to look at. And you're trying to do some predictions about how the temperature, so we're only looking at the temperature, okay, in that particular room. I hope people can see my mouse. So this is the only thing that we're looking at. You can completely disregard the rest of the parameters because there's no, even if there is some correlation, we're not using that. So based on the past values of the temperature.
The screen is not shared.
Screen is not shared. Oh, I'm sorry. Somebody should have pointed that out a little while ago. Okay, so so this was the homework assignment, and as you can see, let me, yeah, that's fine. So as you can see that this has got bunch of data that I'm going to be, I've shared with you. It has room numbers and it has the temperature. And the variation is basically based on, and let me just show you something so that it'll become a little bit easier for you. So this is an actual graph of homework of what the 2 databases look like, 2 data sets. It's not very large, so you don't require a lot of training, a lot of resources. On the horizontal axis, as you can see, there is time over here. On the vertical axis, what we're seeing is temperature. Okay, so this is the first one. This is version 3. And as you can see that there are certain variations and these are happening fairly frequently. I think the period between these is about 12 minutes, if I remember correctly. Okay, so you can see this starts at 24:08, 15, and then 30. So this is occurring after 15 minutes, and then 45. So every 15 minutes, this is just my display. This is not something that you will be, you need to get Python to produce this for you. But once you produce this, you'll see the variations in temperature varying over, let's say, every 12 minutes or so. Now, the idea is that the blue line over here shows you the actual data that I've given you. And the red line is actually my prediction. So I'm actually showing you part of the solution. So this is my predictions. And I hope that some of you can do a better job than I have. So as you can see that and I've used an LSTM network. So you can use LSTM we've already covered LSTM. If you want to get a better idea of how to actually do some encodings in LSTM, I would recommend that you take a closer look. Hopefully you've looked at all of the lectures of Jeff Heaton. But if you notice that in lecture number 10.1 and 10.2, he starts talking about LSTM. Okay, so programming LSTM with Keras data. Okay, so take a look at that, but that won't necessarily give you the solution. You need to find perhaps online, as I've always suggested that there's a lot of code available online, so you should try to find solutions online which use time series predictions, and there are other methods as well which you might be able to get hold of. As I said, LSTM is just one algorithm. So you can see that in my solution, I start predicting from this particular point. So the red portion is the predictions, and it has been able to, based on this past data, you're not training it obviously on this data over here. What I've basically asked you to do is to take, I think, about 24 or 48 minutes, the last so many minutes, and exclude that from the training, and then use the past data over here to be able to predict the rest of it. So what you see here is that it's learning, this particular prediction has learned the particular pattern and is doing a reasonable job. And obviously there are variations in each one of these, so it won't be able to predict exactly the future, but it's done a reasonable job at being able to predict when it's going down and when it's going up. So the red and blue are fairly overlapping. Although some over here, there is some mismatch. So you should be able to determine the accuracy and so on. Now the second data set is a little bit more complex. And can somebody tell me why it seems to be a little bit more complex? I'm trying to get some interaction with all of you. So
the pattern varies.
Yeah, so the pattern is clearly varying. So what you see is that in some places, this pattern is very different from this pattern over here. So when you're trying to predict over here, ideally, if you remember what LSTM is supposed to do, it's supposed to detect different stages. So if you're using an RNN network, it probably won't be able to do a good job. But if you're using an LSTM, it should hopefully be able to understand that, okay, now we're in the long variations, the larger variations, we're not in the short variations. And based on the past experience of long variations, it should be able to do a better job, okay? So my predictions are not perfect, as you can see. I didn't try to optimize it completely, so you can see that it is not exactly matching with the points where the data is going up and down. So I hope that some of you will be able to do as good a job, and hopefully some will be able to do a better job at being able to predict the future. Any questions?
Sir, why are जी सर यहाँ पे टाइम स्टैम्प्स नहीं given है क्या इस डेटा में टाइम स्टैम्प्स नहीं?
So say that again. I'm sorry. What is the question again?
I cannot see time stamps in the second data.
Okay, so somehow that it's there. So maybe it's showing up slightly differently because the timestamps are longer. Okay, so
okay, sir.
It's supposed to be, it's somehow, I just realized this, it's somehow converted into different numbers. So, but basically these are timestamps over here. Okay. Because it was longer, maybe it got cut off or something like that. But the idea here is in this course is also to give you a realization that this is not a completely theoretical course, it's a practical course. So these variations are, just to explain this to you, these are variations because there is, your air conditioning. This is a room with an air conditioning and it's actually set to a certain temperature. So maybe the temperature it was set off at was 25 degrees centigrade, Celsius. And so what it does is, as you know how a thermostat and air conditioning works, is that the compressor turns on, the compressor turns on and the temperature goes down. Actually, the temperature is probably set to maybe 23 or 23.5 degrees, right? Not over here. So the temperature goes up and then the compressor turns on, the temperature goes down, it probably overshoots the value. And then after a while, when it gets too low, it turns off, the compressor turns off, and then the temperature starts rising, and then you start feeling hot. And then at this point again, internally the thermostat realizes that the temperature has gone way above the target value, and then it starts turning on and it starts cooling. Okay, so this is the normal variation in a typical AC. Some of the newer ACs are better. They're based on inverter technology, and they actually do a much better job at keeping the temperature a lot more constant instead of these large variations. Okay. So any further questions about this? If not, let me just remind you that the homework number, the second part of the project is also now due. That's due a week later. And in this part, as you're already familiar, just like before, you're supposed to give a presentation on the 8th, and then on the 10th you have, the presentation is on the 10th, and on the 8th you have the second part. In this, basically, you're supposed to focus in on, you've already done the literature review, but now the focus is on preliminary results, okay? So hopefully you should be able to get some reasonable results at this stage. And in the final part, we'll go over, you'll have an opportunity to share your final results. Let me also take a few minutes to discuss the possible dates for the final exam and for the final project presentations. Are people okay with the concept that if we have the final exams are sometime between 31st and the 9th, I believe. Would people be okay if after the final exam, we have the final project presentations, or your final assignment is due after the final exam? Or do people have to go somewhere?
No, sir, I would be okay with that.
I'd be okay as well.
Okay, so if people are all right with that, most likely that will give you some extra time to actually finalize your project. And so we will take, the final project and the presentation and the paper can be due after the final exam, maybe about a week after the exam. I have to submit the results by about the mid of January. So I will need your final papers maybe the week of somewhere over here, which is maybe just before the 15th or so. Okay, the week of 14th, let's say. Okay, so that was a little bit about the homework assignment and the projects. Now let's get back to our class for today. Right, so we've already spoken about LSTM and GRU. So this is as usual, my just review of the slides. So on these past slides, which I've got over here, slightly cleaned up. And then let's see if I can get rid of this. Somehow I'm not able to get rid of this today. Anyway, we'll try to live with that. It just hides the top a little bit. So we spoke about autoencoders, and we saw that it basically has, an input X over here, an output, and there's a bottleneck in the center, and essentially you have a loss equation, and the loss equation is basically trying to reproduce, look at the difference between the actual input and the output that was produced after the decoding, after the encoder and the decoder network has gone through and there's a bottleneck. And we looked at the variational autoencoders as well, and the difference with the, so can somebody explain to me what the difference was between a variational autoencoder and a regular autoencoder? Anybody can speak up?
It's the training data is based on the distribution of data, and it takes from basically from the probability. It includes the probability.
Right, right. So in the probability, what all are there? So it's got, when it's looking at the probability, what all does it have? What
So
it has
distribution.
It has the distribution. Well, it doesn't have the completed distribution because you understand that a distribution is fairly complex. If you're looking at a distribution of a random variable, if you're looking at, for example, a Gaussian distribution, it looks fairly simple. But if you're looking at a real distribution, it could be extremely complicated, right? So you can't have the entire distribution over there. What it does is it has two parts of the distribution. It has what? The mean and the standard deviation, okay? So it's only using the mean mu and the standard deviation. That does not capture the entire distribution, right? So if you look at this distribution, clearly you can't reproduce it simply by the mean and the standard deviation. Once you have the mean and the standard deviation, at best what you can do is you can say, well, I assume that it's a Gaussian kind of a distribution and this is where it is, so it might be able to approximate it like this. But to get the entire distribution, you need a lot more data, okay? And if you have a probability or stochastic course, you'll be able to go into that, but let's not do that. We also saw something called a KL divergence. I didn't really talk about it, but this is going to appear again because of what we're going to talk next. So just keep in mind this particular equation, okay? So, and then there was a reparameterization trick, which we've already covered. I won't go into that. Now, I'm going to talk about one more autoencoder, and this is what is referred to as a disentangled variational autoencoder, okay? So it builds up on the original autoencoder, which was then we added variations and made it stochastic, and now we're adding something on top of it, okay? And here's the idea. Basically, if you remember, what we're doing in autoencoders is that we're trying to reproduce the data. The original data is being trying to reproduce, and we're trying to somehow learn in this bottleneck over here some kind of representation of the data, which is a little bit more, hopefully more compressed. So if you have a bottleneck over here, you're trying to learn the key components of that data, okay? So if you can think about, can you think about when you could actually do that and be able to reproduce the data accurately? So when would you be able to take a very large data, compress it, and be able to get the original data without any loss? When do you think that could be possible? Somehow I've lost, I can't see people's faces anymore. Still getting used to this system. Show video panel. Okay, so that's better. So can somebody explain to me, when would you be able to take data and compress it and without any loss, reproduce it and have some compression as well?
File compressions do have this.
So I'm not exactly following you. Somebody wants to speak up? Aftab, maybe? So the question again is, if you have original data, let's say a 1 megabyte file, all right? Let's say this is an image, and you compress it using, let's say, zip, okay, or RAR, one of your favorite compression algorithms. And you see that the 1 MB file becomes, 0.5 MB, okay? And then you uncompress it, and it becomes 1 MB again, okay? So my question is that in some cases, this after compression, it may not have any compression. It may, from 1 MB, it may become 0.9 MB, right? In some cases, it might get compressed a lot, okay? So why do you think there is a difference? In some cases, it can be compressed without any loss. In some cases, it can't be compressed.
Maybe it's due to the features, the
Hello?
number of features.
सर ये इस वजह से भी होता है कि
GOS. आपका माइक म्यूट हो जाता है मेरे ख्याल से. You start speaking.
I was going to speak. I was saying that maybe it's due to the features that are present in the picture, the number of like important things, so that it can be like if there are two features or important points, then it will be a little more compressed as compared to a 5 feature.
Okay. Or anybody else?
Am I audible? Yeah.
Anybody else wants to give it a shot? Why do you think some files can be compressed a lot and other files can't be compressed? Anybody who's done, taken a JPEG or an MPEG and tried? जी, वैसा आप बोलिए, आपका mic mute नहीं हो जाए. जी, go ahead.
हेलो
जी, Awais. Can you hear me, Awais? Go ahead. Okay, we're having some trouble.
हेलो
I think Awais is not able to hear us. And
हाँ सर ये मैं कह रहा था कि सर आपने एक बात बताई थी कि एक इमेज को हम कितना कंप्रेस कर सकते हैं कि आखिर में हमारे पास मैक्सिमम 5 फीचर आ जाते हैं. तो सर मैंने आपसे पूछा था कि आप अगर 2 फीचर्स तक ज़्यादा कंप्रेस करें तो सर आपने कहा था वो जब उस पिक्चर को दोबारा डीकंप्रेस करेंगे तो पिक्चर बिल्कुल ख़त्म हो जाएगी.
right,
तो
right.
सर ऐसे हमारा जो डेटा ज़्यादा से ज़्यादा कंप्रेस जितना हो सकता है सर उतना कंप्रेस वो करेगा फाइल. बस वो ज़्यादा हमने कंप्रेस किया सर, डिसकंप्रेस के बाद वो हमें फाइल उस कंडीशन पे नहीं मिलेगी जिस कंडीशन पे हमने इसको कंप्रेस किया था.
Right. So there are two types of compressions, right? There's lossy compression, right? And there's lossless compression. So if you're trying to do lossy compression,
Yes, sir.
and obviously it does depend on the number of features that you're trying to capture. If you try to compress it a lot and try to decompress it, you may only capture the primary features and lose a lot of the fine details. Now, if in some case you can also do a lossless compression, right? You can do a lossless compression in the sense that the file itself may not be in its original format, may not be very highly compressed. So for example, if you have an image, let's say the image is completely black, okay? And let's assume that the black is given as a 0, okay? So all the pixels are all zeros, okay? This could be 1,000 by 1,000 image. Now, do you think that can you compress this a lot? Do you think this is highly compressible?
Yes, sir. Yes, sir.
Right. Versus another image which has a lot of variations, right? There's a lot of things going on. Maybe there's a football match going on with a lot of variations, right? So there's zeros, ones and zeros all over the place. So this, when you compress this, you won't be able to compress it a lot. But since this particular image has a lot of zeros, it can very easily be compressed. There's something called run length encoding. And all you can say is that if there are, let's say, 1 million zeros, all you can say is there are 10 to the power 6 zeros, and that's all you need. You can simply say that the next 10 to the power 6 pixels are all going to be zeros. So that's a very simple way of compressing it, okay? So you can see that depending on the content of the image, you can have a very high compression or you can have very low compression. Okay, it depends on the content. Now, when we're doing compressions, a lot of times we're also doing lossy compressions. In fact, most of the things that we've discussed earlier, if you remember, well, I don't have that here, but if you remember the applications of autoencoders, it was looking at noisy compressions with images with noise and trying to denoise it and so on. Okay, so the idea here is that we're trying to learn features which are really critical, okay, which can really be used to describe the original image. So now what disentanglement does, which is what now we're going to be discussing, is it tries to find out what are those features which are very unique in a sense, okay? And the way mathematically you can describe that is that it tries to find those features which are uncorrelated, okay? So here's an example. This is an example where an image has been generated, and it's generated by changing 4 factors. Okay, it's changed 4 factors. The Y location, so you can see that the Y location is changing over here. In this particular image, the Y location is going downwards. Okay. In this particular factor, the X location is being changed. Okay, so here the image is more on the right side. Okay, here the size is changing, so you can see that this image is becoming bigger and bigger. Okay, and now this particular image is also being rotated, so you can see that this is perhaps being rotated in a particular direction. Okay, so what is being done is that images are being created in which these 4 latent factors are being modified. Okay, so we already know what 4 factors are being modified. Now, once those images, once a large variety of such images are created, now we're going to use some kind of an autoencoder, and we're going to try to learn. Going to try to learn if we can try to figure out that what are those 4 parameters that basically represent the X, Y, rotation, and size. Okay, whether they can separately be learned or not. So and the technique, and without going into too much detail in the technique, this is sort of similar to something that we've done before, where in the loss equation we add in a particular parameter and we change the parameter. Where have we seen this before? Does anybody remember where we've done this before? In the loss equation, we add a parameter. Earlier, I think we added alpha, and we used to change that to be able to get certain objectives done. Does anybody remember that?
Learning rate.
Learning rate, yes, that was at one stage.
Learning
Okay,
rate.
then we've also had other more recent examples. In the learning rate, the parameter was R. And then recently, we also did a parameter alpha, which was changed in the loss equation.
Yeah, the regularization.
Yes,
that we...
absolutely right. So in regularization, we had in the loss equation, we added a parameter alpha. And if we made alpha very big, then it would have certain impact. Okay, so the same thing is being done over here. We've added a beta parameter without going into the details of this equation. We've added a beta parameter, and by changing beta to be large, it basically makes sure that the correlation between the parameters that are learned is high. Okay, so let's look at the results of this to be able to understand this. Okay, so let's see if I can pull this to the bottom. This used to disappear. For some reason today, it refuses to disappear. Hide video panel, that doesn't work. Disable notation. I'll have to figure this out separately. Okay, let me just put it over here. So this is, these are the parameters that are being learned. So you can think of these as the neurons, okay? So Z5, from Z1, well, from Z1 over here till Z9 or Z10, there are like 10 parameters. So you can think of these as the bottleneck parameters. There are 10 neurons, Z1 to Z10, which are being looked at. And what this is showing you is basically that if you have, and let's take a look at a disentangled and entangled version, a normal version first. So in the normal version, we've learned all of these parameters, all 10 of these. But when we individually vary a particular parameter, it doesn't have any specific impact. It's hard to say whether these 10 parameters correspond to either rotation or size or X values or Y values, as you can see, because in all of these, you don't notice. And what we're doing here is in this particular column, we're keeping the rest of these constant, okay? We're only changing Z2 variable, okay? So to see the impact of what happens when in this particular bottleneck, we change one of the neurons, okay? So we change this particular value. We can't really see a particular relationship between this particular parameter and the output image, okay? So these are all the output images. But now let's take a look at the disentangled version, okay? So the previous one was the entangled, this is the disentangled. So in the disentangled, what you're seeing is that Z5, if you vary that, what is being varied over here? You can clearly see that is the Y position which is being varied. Is that clear to everybody? Okay. As you're varying Z7, G. There was a question? GOS.
Sir, in the last picture, there's also a size increase in the picture. Why? In the position
in this
Y
particular case,
images.
in the entangled case.
No, sir. In the disentangled
Okay,
case.
so in the disentangled case, what you're seeing here is that when you're varying Z5, it's only changing the Y position. When you're varying Z7, then it's varying the X exactly as it was the original data that was used to generate these images. It's actually able to capture those original variables. When you're varying Z4, it's changing the size of the object. When you're varying Z9 and Z2, it's changing what seems to be the rotation. So, you know, either the X direction of the rotation, you can have something rotate in 3 dimensions. So it's capturing through 2 of those dimensions. Did that answer your question, Wes?
Yes, sir. Okay. Yes, sir.
Okay. So what we've seen is that now the rest of these variables are not being used. Why? Because in the loss equation, we had a parameter, in this particular case, beta is equal to 4. And in the entangled version, beta is equal to 0. Okay. So in the disentangled version, what we're seeing is that it is uniquely capturing 4 neurons. And these 4 neurons now correspond to certain physical aspects of the images. You know, there's corresponding to the changes in Y, X, scale, rotation, or actually 5 parameters over here. Okay. The rest of the parameters, the rest of the neurons are actually not used. Okay, so it's not using any one of these. So now, why do you think this is important? By disentangling, what have we been able to achieve, and why is this important? Can somebody try to answer that?
We have added weights for these parameters, so it helps
Yeah, but you see, we've also added weights in the other case. So if you look at the entangled version, we've got 10 variables, and you know, each one of them essentially correspond to some neurons which are being used. Okay, so all of these. So let's say you have Z1, say Z10 in the entangled version. So this is the disentangled version, and this is the entangled version. In the entangled version, you're using all 10 neurons. In the disentangled version, you're only using 5 neurons. Okay, and these 5 neurons, we've been able to determine that they actually correspond to some physical feature of the original image. So why is this useful? Why do you think it's useful? Can you think of possible ways to utilize this?
सर मे बी हम ये जो ड्रॉप आउट वाली एक केस है कि कौन से न्यूरॉन्स जो हैं वो भी मतलब हमने डिटरमिन कर लिया कि ये वाली न्यूरॉन्स जो हैं ये कॉरेस्पॉन्ड कर रही हैं लाइक जो हमारी इमेज के ऊपर एक्शंस हैं उससे so maybe we are able to we can use a dropout technique over here to just hibernate the rest of the neurons and use the first 5 neurons.
But you see, dropout is quite a different technique. What dropout does is basically it says that the reliance on, you know, if you're doing, let's say, the typical dropout, what you're doing is that you reducing the reliance on a particular neuron, which is what we did when we did dropout, right? But here what we're doing is we actually taking an image, we're trying to encode it and trying to decode it, right? We're trying to reproduce it. And what we've been able to do is take a large image, a very complex image, and we've been able to represent it in a very small set of variables. So the set of features over here is only 5. So this image that we probably presented over here may consist of millions of images. But after we did the disentanglement, basically what we've been able to see is that there are only 5 features which were really key. And if we know what those 5 features are, we can actually compress this image a lot. So you understand that in a sense, we've been able to compress this into a much smaller set of features rather than a larger set of features. Okay, now this 10 could have been 100 or 1,000 as well, if we weren't careful. But when you're doing disentanglement, it's been able to figure out what are the key features in that image, in that entire image set. Okay, so if we take a look at some further results, so this is a comparison. Again, it's showing you the changes over here, versus you can see that these variables don't really correspond to any particular feature, whereas it is still, all of these are still useful in being able to uncompress the image, but there is no specific relationship between Z2 and any physical feature, any physical aspect of that image. Now this becomes a lot more interesting when we look at other examples. So here's another example. And by the way, a lot of times, if you notice that I do give references, okay? So this is a reference that I've used, and a lot of times it is based on YouTube videos. So if you, I would encourage you, in addition to listening to the Heaton lectures, also refer to the references that I often give. Okay, that will also help you understand. So if you look at this particular case, so this is an example where disentanglement has been used, and a large number of images were presented. And after disentanglement, it learned 1, 2, 3, 4, 5, 6, 7 latent features. Okay, And each one of those latent features, when you keep the others constant, okay, you keep the rest of them constant, and you make a change to any one of these, it turns out that, if you look at this, you can see that the background of this image is changing. The color of this background is only changing. Rest of the image remains exactly the same, okay? When you change this particular parameter, it is actually doing a turn left, okay? So you can see it's sort of like you're looking at the image and you're turning in a particular direction, okay? This is sort of a turn right. This corresponds to distance. So you can see that as you're going further away, the object becomes smaller, okay? This is looking at other objects, rotation, object ID. So here, if you change this, the actual object is changing, okay? So this is a very useful feature of autoencoders to be able to disentangle the variables. And as we go further down the road, as we go into generative adversarial networks, where we want to generate images, you can imagine that this could be useful. So for example, if you're trying to generate images, and all you're trying to do is just make one change, then you know that if you change this particular variable in the encoding, then you could actually change the background only. Okay, so this will come in handy as we go forward. Here are some more examples. So these are examples of facial features. So this is the entangled version. This is the disentangled. And what you can see over here, can somebody tell me what's going on over here? Why is, what do you notice between the entangled version versus the disentangled version in the images? And look at it going horizontally, okay? G.
A full feature is actually like her hair is actually being removed and then back. So
say that again. I didn't quite
compared to
catch
the
you.
other picture, you can, yeah.
Yeah.
I said that a whole feature like her hair it has been identified and compressed, like it isn't there in the middle picture and then it comes back. And in the right one, it's just like it's not actually recognizing the whole thing. So in disentangled, as you mentioned, that a whole background, you can like change it, or
So
maybe that's what's
so
happening.
let me explain it to you, and maybe that'll become clearer then. What's happening over here is that you're rotating the face. So this particular variable over here, let's call this Z1. By changing this, you are able to take a particular individual and change the direction of the face. Now, if you notice that in all of these, the face more or less is the same. In each one of these, the face remains the same. The only thing that is changing more or less is the direction of the face, okay? Instead of this person is looking in this direction, here the person is looking in this direction, okay? Now, we try to do the same thing over here in the entangled version, but look at this, what happens over here. What do you notice over here? Yes, the people's faces are changing the direction, but what do you notice over here? What else is changing? Can you notice something? What other feature is changing over here?
Eyes. And
yeah, exactly. So this person, the glasses, he didn't have glasses, and then all of a sudden the glasses are also coming in. Okay, so even though all the other parameters were kept constant, only one particular parameter was changed. However, in the entangled version, not only does the face direction change, but also other parts of the facial features change. And that's because it's entangled, okay? And this is the entangled version. In the disentangled version, what you notice that you don't see that happening. You don't see somebody all of a sudden the face changing. In other words, the somebody putting on glasses, or even if you look over here, some other features are changing. So if you look at this further example, so this was referred to as azimuth rotation. if you look at this, now what they're also doing is changing the smile. So hopefully you can see that people over here are either in one direction smiling or not smiling. It's a bit hard to tell. But what you can see over here is that other features are also changing. Okay, again, glasses are changing. This is the entangled version. This is the disentangled version. And you can see that other features are also changing. So if you look over here, the hair, so this is the hair fringe. So you can see that the amount of hair is changing over here. But in this case, you can again see that not only is the hair changing, but other features are also changing. Okay, so that's the basic idea of disentanglement, which is becoming quite an important area for images and for a variety of reasons, as we see when we go forward. So any questions about this particular topic before we go on to a completely different topic? So this sort of closes the broad topic of variational autoencoders. Now we look at a slightly different type of autoencoder as well. But any questions? Okay, if none, let's keep going. Let me make sure. What's the time?
हेलो सर
जी
सर, ये जो अपने वेरिएशन एनकोडर जो है डिसएंटेंगल वाला वर्जन, सर इसका थोड़ा सा जो पैरामीटर यूज हुए हैं फॉर्मूले के अंदर, वो आप थोड़ा सा बता देंगे?
Okay, so here basically what's happening is that this particular formula, I don't want to explain this because they'll require a lot more detail than I'm ready to discuss right now. But basically this parameter over here is called KL divergence. And this is a parameter which basically compares two distributions. So let's say that you have one distribution which is looking like this and another distribution which is looking like this, okay? Now you can see that both of these distributions are very similar, okay? So that means that they're not very different, okay? But suppose that you have another distribution which is completely different, okay? So you can see that these two distributions are very different. So the KL divergence basically measures how different two probability distributions are, okay? And by making this parameter beta large, what we're basically saying is that we want the two distributions of, let's say, Z1 and Z2 to be uncorrelated. We want them to be very different. If they're very similar, then it will only utilize one of those variables, one of those latent features, either Z1 or Z2. It will drop one of those because it will say, well, they're essentially the same, okay? But if they're completely uncorrelated, then it will pick both of them. It will only pick them up if they are uncorrelated, okay? But to be able to truly understand this, we will have to go into a lot more into probability and stochastic processes than we've actually studied so far. But if necessary, we can go into have a separate discussion on that maybe in one of our later lectures if you have time. Okay. So let's go on. The next topic that we're going to discuss is something called RBMs and DBNs. These are referred to as restrictive Boltzmann machines. Okay, it's quite a mouthful. And DBNs are basically a deep version of RBMs. Okay. Now, the concept behind RBMs is quite useful, and it's something that has been used in the past and is still quite often used. But the reason that we're talking about it is because it has some very unique properties which are different from what the typical artificial neural networks that we've talked about so far. Okay, so it is an artificial neural network. Okay, but it has two major differences. The first difference is that it is of a probabilistic nature. Okay, and the second difference is that it uses energy models. Okay, now what does that mean? I'll discuss that as we go forward. Okay, and its claim to fame basically was in 2009. Netflix, some of you might have heard of this. Netflix, I presume all of you are familiar with Netflix. It launched a major competition, and the competition was on something called collaborative filtering algorithm, which we'll talk about. And the idea was that if you have data from, let's say if you have a bunch of movies, all right, and you have a bunch of users, okay? Now, each one of those users typically can rate a movie, okay? So let's say you have movies 1 se lekar ke M tak, and you have users 1 se lekar N tak, right? Now, user 1 may give a rating, let's say the ratings on a scale of 1 to 5. Okay, so user 1 may give a rating of 5 to movie 1, to movie 2 it may give a rating of 1, let's say, to movie 3 it gives a rating of 3, and so on. Similarly, other users can give different type of ratings. So maybe user 4 or user N can give a rating of 1 over here, rating of 3, rating of 2, and so on. Okay, so Netflix has all of these. And what happens in recommendation engines is that whenever you log in, let's say whether you're logging onto Amazon, or if you're logging onto Facebook, or you logging into YouTube, you get a bunch of recommendations, right? So you go onto YouTube, and it automatically gives you a bunch of recommended YouTube videos, right? So all of that is done using recommendation engine. And the idea of this Netflix competition was that it wanted to, based on the existing data, it wanted to say that, well, if there's a new user, let's say you have a new user, N+1, okay, and this particular user gives a rating of, let's say, 5 to this particular movie. It gives a rating of, let's say, 2 to this particular movie. Now, it hasn't rated other movies. Now, the idea was, can you predict what this particular user would give, what rating would it give to this particular movie? Okay. Now you might say, well, it's very similar to this particular user because he also gave a 5 over here and he gave a low rating to this particular movie. So he'll probably give a 3 over here. Okay. So the concept here of collaborative filtering is that you find out what other users you're similar to, and then you use their data to be able to predict your unknowns. Okay, so can you see why this would be extremely useful? And can you think of all other examples where this could be used? Can people give me other examples that you're already using?
Sir, any kind of recommendation systems?
Yeah, any kind of recommendation engine, recommendation systems. And can people think of other examples that we've already spoken about?
Online
Medical.
shopping.
Yeah, on all kinds of e-commerce, whether it's Daraz or, what have you, or Amazon. Okay, so you can see this is an extremely important area of neural networks and AI is recommendation engines. This is where actually a lot of money is made. Most of the big companies are already using this, and that's why you can imagine why Netflix gave a prize of $1 million to any individual who was able to beat their algorithm by more than 10%. Okay, and there was a winner in this particular case. There was an AT&T group which actually improved their algorithm by something like 10.01 or something, slightly better than Netflix's actual algorithm. Okay, and they used RBMs in that. So that is the important thing. And that's why RBMs are still used. In fact, apparently Netflix still uses RBMs. Now, you might say, well, why do we need a new algorithm? Can I use autoencoders, the existing autoencoders for this? Do you think you can use that? And how would you use that if you wanted to be able to predict unknowns over here? How could you use your standard autoencoder for this kind of prediction? Any ideas? So you have your standard autoencoder, which is taking, let's say, all your data, okay, and it's compressing it into, important features, and then it can expand this again. So can we use this concept to be able to learn important features about why do you think that these two guys are similar, first of all? Why do you think that if this chap rated this particular movie a 1 and this particular movie a 5 and this particular movie a 1, do you think there was some inherent feature about these two movies, which is why these two people were rating this similarly?
So maybe the genre of the movie.
Yeah. So maybe the genre of the movie was, it could be maybe these two guys are into horror movies. So this is maybe a horror movie. And that's why both of these guys are into horror movies. This may be something like, a romantic movie, and these guys don't like romantic movies. So they both gave a low rating to these movies. Now, in this particular case, let's say this was not a 3, this was another 5. Now, if this was a 5, then most likely this was also similar. This had the same kind of genre, right? This was maybe also a horror movie, or a lot of action movie or something like that. And so these two people might be similar. So what's going on over here? Can you see the relationship between the ratings that people are giving and some latent features of these movies?
So this is.
So we are treating the missing values as noise.
No, but essentially, what are we learning? So if we use an autoencoder, okay, and we try to learn certain aspects of these movies in a much condensed way, then what do you think? Let's say if we try to learn certain key components of these movies, in this particular example, what do you think we would be learning in this particular example?
Like the features, type of movies, or
Yeah, exactly. So we essentially saying that if we were somehow able to learn in the autoencoder, we could learn, we could have a parameter Z1, Z2, and Z3, and this could tell you the genre of the movie, which means, let's say if it is a 1 or a 0, this implies that this is a horror movie or not, okay? And Z2 could imply that this is a romantic movie or not. Z3 could be, is it an action movie or not? And if we could learn these features, these hidden latent variables about the movies, and we could somehow be able to figure out that this particular user, what is his relationship, or what if we have a new movie coming in, we could figure out what type of movie it is based on the past ratings of these movies by earlier people. Then maybe we could figure out what a new user, let's say this person only likes action movies, and we can figure out that a new movie is an action movie, then we could easily figure out what his ratings would be for other movies, which we can easily categorize. And we can categorize all of these movies as action movies, okay? So I hope you're getting some idea as to what we're trying to do. by learning in the autoencoders, we're trying to learn you can even think of these as disentangled features, that we're trying to learn in the disentangled features, we're trying to perhaps learn the type of movie. Okay, it could be the type of book, it could be the type of clothing article, or what have you. All right, so let's see how somebody, Hira has your hand raised. Please go ahead, Hira.
सर मतलब ये मेरा ख्याल हो सकता है मैं गलत हूँ. ज़्यादातर जो ये एंटरटेनमेंट जो वेबसाइट्स हैं उनका बेसिक पर्सपेक्टिव जो इन चॉइसेस के बीच होता है, they are working on personas, that how do you behave in certain conditions and what kind of entertainment do you like. So mostly जो वो क्लासिफाई कर रहे होते हैं, वो जो है वो पर्सोनास क्लासिफाई कर रहे होते हैं, उसके बेसिस पे आपको आपका परसेंटेज मैच पता चलता है कि आप जो मूवी देखना चाह रहे हैं उसका कितना परसेंटेज मैच्ड है आपके पर्सोना के साथ. That's my understanding. Maybe I am wrong.
जी. So this is something very similar to what we're talking about. They essentially, by saying that this particular user is of a certain type, right? Now, this particular user may be of a certain type. So for example, if we talk about 3 types of movies, horror, romance, and action, right? So this particular user, let's say his persona, if you might call it, is that he likes horror movies, he doesn't like romantic movies, and maybe he likes a little bit of action movies, okay? Now, if we can find out for another user, okay, how does he fit in? Maybe there's another type of user, okay, who only likes these kind of movies, all right? He doesn't like horror and action movies. Now, let's say a new user comes in, and now what you're trying to figure out is what type of a user is he, all right? Now, if he comes out to have this kind of a persona, all right, then we can immediately say that anybody who has, if this particular type of person, whichever movies they have recommended, or all of these users, there could be hundreds of users in this category, all the movies that they have recommended should be recommended to this particular person, okay? Because we've actually figured out what kind of a personality that person has, okay? So I think that's pretty much what you're saying as well. Do you
Yes,
follow?
sir.
Okay, so
Yes.
that's what we're trying to do, is we're trying to fit individual users into certain categories, okay? And the way we're learning it, the way we're doing it is by being able to figure out what kind of a personality they have, or what kind of personas, what kind of hidden features about the movies they prefer, okay? But because notice that these features are not known to us. We don't really, in the olden days, what used to happen is that Netflix would actually ask users, how do you rate, what kind of movies do you like, all right? And they would give them a questionnaire, maybe 20 different questions as to, do you like horror movies, do you like action movies, do you like this, blah, 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 and so on. And then they would, once they've specified themselves, then they would do the recommendations, okay? But now what's happening is that based on the ratings that individuals have given to movies, you use that data to train your neural network. And then the neural network basically gives you the recommendation as to what is the probability that this particular person will like a certain movie. Okay, so that's what in general, in the direction that we're going in. And this can be done using a variety of techniques, okay? And, but basically the way this needs to be done is using the technique of autoencoders, okay? Now let's take a look at RBMs. So RBM is reasonably similar to autoencoders. And the simplest case of the RBM basically has 2 layers, okay? You can think of this as a 2-layered neural network. It has the input, all right, the input over here, and then the hidden layer, okay? So the input layer comes in, and the hidden layer generally is smaller, so it might have much fewer neurons, because we're trying to sort of learn the important features, just like we've been doing in autoencoders. We're trying to learn certain important features about the input, okay? And then we're going to use it in two ways. Okay, and this is a little bit different from the normal way. If you look at the autoencoder, if you look at autoencoders over here, an autoencoder would take inputs X. Okay, it would have a hidden layer. Let's say this is an autoencoder with only one hidden layer, and it would generate an output. Okay. Now the RBM is doing something similar, and it's also trying to learn if this is the input X and this produces the output Y. Here, what do we normally do? We take the output Y and we do back propagation. And what do we use as a loss equation? We use Y minus, what do we compare the output Y with?
X.
We compared with X, right? Why? Because we're trying to reproduce the output. We're trying to make the output as close as possible to the input Y, but with using a small enough bottleneck over here so that we learn important features. Okay. Now, the way RBMs are different from autoencoders is that it doesn't have the output being given over here. It sort of does it in this way. It goes forward and then it goes backwards. Okay, and it does it in a number of iterations. So just like we're doing iterations over here, it just does it without having an output layer. The output layer is actually it's just done it in a reverse way. It's just a different technique. It's an older technique, but it's still in use. Okay. The other way it's different is because here the loss equation is Y minus X squared. Okay. And this is a major difference. Instead of using a loss equation, what it does is it uses an energy model, okay? An energy model. And this is something which is completely different from anything that we've studied so far, okay? So what it does is, first of all, the weights will be the same, as I said, in both directions, okay? The other thing that it does have is it has these biases. Okay, so you have biases for the visible layer, okay, and you have biases for the hidden layer. Okay, so these are the two biases which are going to be used. So let's try to understand what the energy equation will be. Okay, so the energy equation basically says that we will take the multiplication of the input V. Okay, so this could be some input. So this could be an image. It could be a movie rating or what have you. Okay, we're going to take V sub I and we're going to multiply it by the weight. What will the, and we'll multiply it by the weight Wij. Okay, and then we'll multiply it by the hidden variable H of J. Okay, and we'll sum this over all possible what? What should we do a sum over? Any suggestions? Because we want to calculate an overall energy. So we're calculating the energy of the entire network. So what should we sum over? Well, you can see that I over here corresponds to the input variables, right? So let's say we're going from 1 till, I think I've used some parameter earlier. Let's say we're going over N, and this is M. Okay, so if you want to calculate, do the sum over the entire network, what would be going over? Any suggestions? Not too difficult. If you're trying to go over the entire network, what Well, we clearly wanted sum over all the possible i's. Okay, so we want to sum over all possible i's. So we will do a sum over all possible i's, I from 1 till n. And we also want to do a summation over all possible j's as well. Okay, so we're going to do a summation from j is equal to 1 till m. All right. So this is the starting point. However, and we're going to put a negative sign over here because we want to make it smallest. We want to minimize the overall energy. And we're going to have two more terms over here. We're going to have another term, which is basically the bias term over here. So what do you think the bias term should be? We want to take the variable vi and multiply it by what?
AI?
Right, AI, did you say?
Yes.
Okay, very good. And then we're going to have another bias term, and we're going to take something over here. What should we have over here? So you calculated the biases over here. Now we need to calculate the biases over here.
HI and J.
H of J of B of J.
Hj and B of j, right?
Okay.
So we've got Hj and B of j. So we're summing over j over here, summing over I over here. Okay. So that's basically something called an energy equation. Okay. Now this is how it's defined. So we're not deriving this, we're simply defining this, and this is part of the model.